Some people will tell you that climate change is really complicated. Other people will tell you, well, it's not really a big deal. Yet other people will tell you, well, maybe it's important, but there's nothing you can do about it. So why bother? Today, on this Earth Day 2018, I invite you to think again about climate change. Because the science behind climate change is simple. The impacts of climate change are serious. And the problem of climate change is solvable. So the science of climate change is simple, and it boils down to these three key facts. Number one, CO2 traps heat. Number two, we've added loads of CO2 to the atmosphere by burning fossil fuels. And number three, as a result, the world is getting warmer. Three simple facts. And we're now going to dig into the nitty-gritty, some of the physics of this, and we're going to do that through the medium of dance. So, climate is all about heat energy. And the ultimate source of heat energy that drives our climate is the sun. That heat energy travels to Earth through space in the form of waves of visible light. Those bouncing waves of light collide with the atoms of the Earth, and when they collide, they make them bounce around faster. And in turn, those bouncing atoms can re-radiate some of their heat back into space. You felt this if you feel the warm ground radiating heat on a hot day. Now, that heat radiation that's given out from Earth is in the form of infrared radiation. And infrared radiation has this kind of slower, cooler dance move than the incoming visible light. And as a result, the CO2 in the atmosphere, which dances like this with its one carbon atom and its two oxygen atoms, the CO2 takes notice. And it can absorb that infrared and start vibrating faster itself, and then can re-emit that energy back down to Earth, which can reabsorb it again and re-emit it back into space, where it can get caught again by CO2 and sent back down to Earth, where it can again warm up the planet. So the more CO2 you add to the atmosphere, the harder and harder it is for heat to escape into space, and the warmer our planet gets. This is just like wearing a big warm jacket if you go out for a run. You heat up because your body heat can't escape. So, how much CO2 have we added to the atmosphere? To give you some context for this, we're going to take a trip back through geological time, looking at data that comes from these Antarctic ice cores. The bubbles in these ice cores contain trapped pockets of fossil atmosphere. These are perfect little vials of the atmosphere that our cavemen and cavewomen ancestors were breathing tens of thousands of years ago. And what this graph shows you is the change in CO2 over the last 800,000 years to the present day. What you can see is that during an ice age, CO2 is regularly about 200 parts per million in the atmosphere. And there is a kilometre of ice on top of our heads where we are now in Scotland. During an interglacial period, CO2 is around 280, and all of human civilization is concentrated into this stable period of about 10,000 years. What's happened in the last 100 years? Well, the burning of fossil fuels by this reaction has elevated CO2 to the level of 410 parts per million in the atmosphere. That's a CO2 level that we haven't seen on Earth for the last 4 million years. And 4 million years ago, with 400 ppm CO2, there wasn't an ice sheet on Greenland, and there were birch forests on Antarctica. And sea level was at least 10 meters higher. This is the same CO2 rise as that at the end of the last ice age, but it's happened 100 times faster. And we are only just starting to feel its full climatic effect. So let's look at that climate effect. This is global temperature data over the last 100 years or so from NASA. And what you can see is over the course of the 20th century, this relentless rise to higher and higher global temperatures, such that the warmest 13 years on record all fall in the last 15 years. And those record-breaking temperatures are a sure sign of a changing climate. The chance of that happening, if our climate wasn't warming due to CO2, are vanishingly small. 1 in 27 million. For context, the chance of being struck by lightning in your life is 1 in 12,000. This is a surefire sign of a warming world. The impacts of climate change are serious. This map shows, just to recap. The science is simple. CO2 traps heat. We've added CO2 to the atmosphere, and it's getting warmer. This is uncontroversial. We've known this for more than 100 years. And, as I said, its impacts are serious. So, this animation shows global temperatures over the last 100 years, which, by today, have warmed, on average, by 1 degree Celsius. Now, 1 degree C, that might not sound like all that much, but that temperature change isn't evenly spread across our planet. At high latitudes, so up in the Arctic, temperatures are already 4 degrees C higher than they were pre-industrially. 4 degrees C. It's the difference in annual average temperature between Scotland and Paris. Quite a change in temperature. The reason that we've had this enhanced warming at high latitudes is intimately linked to the behavior of Arctic sea ice. This figure shows September sea ice extent from 1979 to the present day. And you can see that this has dropped by almost half. Now, when that happens, we replace white, shiny sea ice with dark ocean water. And the effect of that is that you can absorb more heat. It's just like wearing a white t-shirt versus a black t-shirt on a hot, sunny day. And so, as the Arctic absorbs more heat, more sea ice melts, which allows more heat to be absorbed, which melts more sea ice, and so on and so on. A positive feedback loop. Now, Arctic sea ice floats, so it doesn't change sea level when it melts. But land ice in the surrounding high latitude regions is melting as well. This is a dramatic image of that. 2 pictures taken from the very same place of Muir Glacier, Alaska, in 1941 and 2004. And you can see the catastrophic loss of this glacier, a pattern that is being seen across the world. And when this ice melts, it flows into the ocean and it raises sea level. So by 2018, sea level has risen by about 20 centimeters. It's about the size of a banana. It's a chunk so far, but it could be much, much worse. So by 2100, recent estimates predict that if we continue burning CO2 at the rate that we're doing it, we could see 1 meter of sea level rise. Why is that a serious impact? The planet doesn't really care. The planet doesn't really care if sea level is 1 meter higher, but people do. The majority of our major cities lie within a couple of meters of sea level. And so a rising sea level displaces those people. The second impact I want to talk about is that of food production. This is a photo taken from the European heatwave in 2003 of a decimated maize crop. In France in 2003, temperatures were 3.5 degrees Celsius warmer than normal. And as a result, we saw catastrophic loss of wheat, maize, and fruit. But to place that in context of where we're headed, I'm going to show you this figure here. In blue are all of the recorded temperatures between 1900 and 2006. And you can see 2003, that extreme heat wave event, indicated with this arrow. In red, I'm showing you projected temperatures for the year 2090 if we don't dramatically reduce burning fossil fuels and the amount of CO2 in the atmosphere. What this graph is telling us is that about half of these projections lie above that most extreme 2003 value. In other words, there is a 50% chance that summer in 2090 will be the hottest ever recorded, with devastating consequences for how we get our food. And the impact is even more extreme in tropical and subtropical countries. So in France, the chance that summer 2090 was the warmest on record is about 50%, shown as this yellow colour here. But this red colour shows us that for the tropics and subtropics, unless we dramatically reduce the amount of CO2 in the atmosphere, summer 2019 will definitely be the hottest of all time. This, again, is a serious impact of climate change because of the people who live in these places. Already today, there are 1 billion people on our planet malnourished, and 95% of them live in these tropical and subtropical countries. So to recap, the impacts of climate change are serious, and I've given you two examples. First, that rising sea levels will displace people, and second, that food production will be massively disrupted and lead to global hunger. I'm going to have a kid this summer. I'm having a baby at the end of June. And this is not the world that I want that child to inherit. But the good news, and this is the most important part of this talk, is that this problem is solvable. We know how to fix it. The root cause of climate change is this reaction, the burning of fossil fuels, which produces CO2 as a waste product. To fix climate change, we need a revolution in how we get our energy. And that revolution is possible because revolutions in human society can happen. As an example, I want you to go back to the end of the last ice age, where there's only a few million people on our planet, and they live as hunter-gatherers. And even with just a few million people, we've already driven woolly mammoths to extinction. Then, at the end of the last ice age, as climate stabilizes, we create a revolutionary new technology. That technology is farming. What farming allows you to do is to use your human ingenuity, to use natural resources, rainfall, sunshine, and to use them again and again and again, such that we can now feed 7 billion people. When it comes to our energy, though, we're still in the hunter-gatherer stage. We go and find coal or gas or oil, we dig it up, we burn it, and it's done. We need to make that next revolution in how we get our energy. Just like we did for how we get our food. Use technology, use human ingenuity to harness the energy of the sun and the energy of wind to get energy again and again and again. And this is happening. Over the last 10 years in Scotland, we have tripled our renewable energy capacity, such that 70% of our electricity now comes from renewable sources. And that's created 26,000 jobs in the process. And China has enough solar panels installed to power all of Scotland 1,000 500 times over. This revolution is happening. Finally, I want to emphasize that individual actions really add up. So for example, think about a 100-watt incandescent light bulb. Left on overnight, that light bulb, if produced with electricity from a coal-fired power station, produces about 1.5 kilograms of CO2, and we chuck that unnecessarily into the atmosphere. Not only does that add CO2 to the atmosphere, it costs you money on your energy bill. Now let's see how that adds up. So if everyone in the UK started with those 100-watt bulbs and switched them to 15-watt LEDs, in the course of a year, you would save 56 billion kilograms of CO2. That's the equivalent of driving around the circumference of the planet 8 million times. It also saves you money to spend on things that make you happy. For instance, you could buy 4 billion of these delicious fudge donuts. So to finish, some people will tell you that climate change is like an oil tanker with this unstoppable momentum forward that you can't do anything about. And I want to dispel that myth. Because human behavior is more like the behavior of a flock of birds, where the action of one or two individuals can influence the action of the individuals around them. That in turn influences the individuals around them and the individuals around them, and all of a sudden, that whole flock can change direction. Thank you very much.